Hello everyone, welcome to my presentation. I'm Stavros Konstantinopoulos and I'm a PhD student for Rensselaer Polytechnic Institute. This work is in collaboration with Nademi and Luigi Vanfretti. The title of our work is Dynamic System Modeling and Stability Assessment of an Aircraft Distribution Power System by implementing Modelica and utilizing the FMI for analysis and design. A few motivating points. We're moving towards more and more electrifying our aircrafts. There are a lot of models and concepts of hybrid and fully electrified aircraft propulsion, and we need to model everything that's included: batteries, electrical motors, etc. However, these components are not standalone. They have cooling requirements, they have a huge impact on the weight of the aircraft, the weight distribution, etc. These things need to be modeled. In order to have complete system integration, we need multi-domain models. We need to consider the thermal management, the aerodynamical behavior, how all these things play together. So we need something that's not domain-specific, a tool that's domain-specific, electrical, thermal, mechanical. We need something that can combine everything. We need a model-based design. Here is where Modelica and the FMI come and give us a huge aid for that purpose. The Modelica is an open access standard. It's a multi-domain modeling language, and it's really suitable for model-based system integration design. So the scope of our work is we're implementing the distribution system of a Boeing 747 in Modelica. We want to distribute an open source system to be used as a baseline for future more electric aircraft multi-domain studies. So someone could use our base system that's electrical and put on top of that the thermal components and other considerations that affect more of their work. We want to exploit Modelica's object orientation and template capabilities in order to have easier time designing the system and testing. With the object orientation and the templates, we can swap controllers, components, generation, loads very easily, and we can add multiple loads and just replace them. It's a really handy tool to just create a lot of configurations that we need to test. We then perform dynamic stability analysis across multiple operating points for our system. When we say multiple operating points, it's mostly loading conditions and how fast the jet turbine is actually rotating, because this affects the frequency we have on the AC side and changes the dynamics. And we then illustrate how the functional mockup interface, FMI, can enable cross-tool simulation and analysis. So the outline of our work is we'll present how we model the power system in Modelica, showing the layout, the templates, how we can swap things, how we can swap parameters, how we can swap the components. We introduce separately the generation, the load models, the generation model, the load models, and the controls for each one. We then go and show how we can just seamlessly use the template capabilities to swap components and compare different configuration. For example, we're going to do a controller different controller evaluation in this work. We then isolate and export parts of the system. We can export the whole system if we want. Through the FMI, import into MATLAB and do a compensator design there. Because, for example, MATLAB and Simulink are one of the most popular tools with control engineers for designing and testing controls. And then we're gonna evaluate the overall performance of the system in terms of power quality, voltage regulation across an emulated flight profile. So initially we have the generation part. In the generation we have a standard synchronous generator, which its rotor is driven by the jet turbine. The jet turbine is emulated here by rotational speed injection on the rotor. So we're not assuming any effect of the generator's loading on the rotational speed. We assume that the jet turbine is strong enough to keep that speed constant. And then we have the automatic voltage regulator on top of the generator. It's taking care of supplying the excitation voltage and keeping the output voltage of the generator very close to the predefined 200 volt set point. So for the loads, every load is decoupled from the AC side primarily with a converter. We have rectifiers rectifying the voltage, and then if we have an AC load, we invert it again through an inverter that's driven by the respective controller. This is due to, because we have variable frequency on our grid, it's not suitable to just connect AC loads on top of the variable frequency. And we need to control how the loads behave. So for these converters are averaged models. There's no switching model in there because the dynamics of the switching are really high frequency. They don't really interfere with what we're looking at here. So for the hydraulic pump is modeled as a standard induction motor. It's connected to a torque load. The fuel pump as well is modeled as the hydraulic pump is roughly 30 kVA as of a load. The fuel pump is modeled as a small 300-400 watt load. It's a small DC motor. We tested it. It doesn't really impact a lot the dynamics or the voltage profiles of the system. It can be just as well swapped by a resistor. For the ball screw actuator, we model it as a permanent magnet synchronous motor, and it's driven by PI speed control, which drives the inverter and tracks the required speed reference. So this is how the template of our system looks. Immediately you can discern that there are sunken boxes across the system. This indicates that this component is replaceable. What we have put in the template is the base class. So the base class is like there's a generation class, a load class, an AVR class, a record class, AVR record, for example, where you see the AVR data on the top right. This holds parameters, for example. If we right-click in any of those components, we can replace it by only components that share the same base class. So it's really easy to swap AVRs, generating units, loads within seconds and create whatever configuration you want. You can add more loads. You can add a lot of ball screw actuators, a lot of more hydraulic pumps, 2, 3, depending on how many engines you have. This is really handy. And we can create very complex models using this template really fast. We have a timetable on the right, which basically is the rotational speed of the jet engine with an emulated profile we designed, and it's fed into the generator. So when we swap everything, this is how our final system looks like. We have the generator giving its outputs to the AVR. Based on these outputs, the AVR designs the excitation voltage, feeds it back in. We have the hydraulic pump that has its own rotational profile, which is a scaled version of the rotational speed of the jet engine, which is expected. We have some auxiliary AC loads that are connected to ground. We have the fuel pump, and we have the ball screw actuator with its own profile to emulate some rapid movements of the ball screw actuator. All the commands are in terms of speed commands. In the synchronous generator, we can see we have 2 inputs and 5 outputs. So any arrow-like output and input indicates that's a real number. So we have initially an input on the right, the omega ref, which basically is the rotational speed of the jet engine. On top we have the AFD, which is the excitation voltage. And we have 4 outputs, which are currents, excitation current, and phase current that are fed to the AVRs for its model because it has to do some calculations for the commutators. On the left, you can see we have the AC output. The excitation is realized through a controllable voltage source because all the exciters and the commutators are modeled with time delays and algebraic loops. So actually modeling everything in detail is not really relevant and it will burden our simulation considerably. So switching to the loads, we have here the hydraulic pump load. It's a standard induction motor. The mechanical load is modeled as a linear torque, as a torque being linear to the rotational speed. On the top right, you can see that the AC voltage is rectified and then it feeds into the inverter. The inverter phases are driven by a VF controller, voltage to frequency controller, which tracks a reference speed with a speed sensor. We're assuming that we're measuring speed here. This is a very standard. We have some start time. We can indicate on the block when we want the load to connect, because it's not really advisable to connect the load when the synchronous generator has not built any voltage. This will be a recipe for disaster. We can let it connect after a few seconds that the voltage has been too close to nominal levels. The next two loads we have is the fuel pump and the ball screw actuator. On the left, you can see the ball screw actuator. Again, we have the same picture. We change the voltage level to make it suitable for our machine. The ball screw actuator, the PMSM, is 2 kilowatts, and it's driven by a PI speed control. Again, the PI speed control takes the rotational speed and then creates references for IQ and ID currents. These are translated to VD and Q, D and Q axis voltages, and then are transferred back to the ABC frame and basically drive the PMSM motor to track the desired reference. Again, the load is a linear torque linear to the rotational speed. For the fuel pump, we have again a rectifier. It's connected to a linear load again, and we have two auxiliary DC loads. In most of the simulations, the fuel pump was substituted with a resistance because it was not really relevant to the dynamics, and the load consumption is really low. Again, in each of the loads, you can notice that there is always a record that's replaceable for the parameters. If we want to swap the parameters, for example, increase the rating of one of the equipment, we swap the records, done.